Good morning, everyone, and welcome to How DC Power Will Transform Building Design and Performance. That's right, we're rewiring the future today, this morning, with Bolis Ibrahim of Sense Power. I don't want to spend too much time talking because you're here to listen to Bolis and not me. Bolis Ibrahim, known him for several years. Lovely person, smart guy. So, Bolis, why don't I hand things over to you right now?
Sure. Thank you, Anthony. And thank you all for being here. It's a pleasure to speak to you all. Maybe some of you have heard me speak before. My name is Bolis Ibrahim, co-founder and president at Sense Power. I've been in the direct current power distribution space for over a decade now. I'm an electrical engineer by education, but an entrepreneur by practice. And I spent most of my time over the last 10 to 15 years working on technologies to bring direct current power into the mainstream. And so we focus on accessibility of direct current power so that we can bring the cost down, bring the safety up, so make these systems safe, um, and make it so that they're more accessible for use in buildings by specifiers and electrical contractors. So yeah, let's have a lot of fun here. Feel free to drop any questions in the Q&A, and we'll pause as necessary, and then there'll be plenty of time at the end for a discussion. Um, but without a doubt, I'll get into it. I'll go over a quick intro. We'll be spending a lot of time on class two, low voltage. Lots of applications there today that we can use today. And then we'll spend the last quarter of the presentation talking about fault managed power, or class four, which is new to the electrical code. It was added to the National Electrical Code, or the NEC, in 2023. And I'm currently on the working group with CSA, bringing it into the Canadian Electrical Code, as well as the technical subcommittees working on the CSA standards. Okay, so a little bit about us. We've done over close to 2 million square feet now of direct current power distribution across several projects all across North America, and now moving into Europe. Lots of really interesting stuff. So large architectural fixtures, general area lighting, telecom applications, but there's lots of interesting stuff happening in the direct current space. And as a refresher, the direct current um, we use today is almost everything. So the computer you're looking at, your cell phone, your laptop, anything with a battery, anything digital, all of that is direct current powered, and it's expected to grow. So it's 32% of consumption today, but expected to grow to over 74% by 2030. And our future generations will be born into a world that's totally direct current. So this goes back all the way to the days of Nikola Tesla and Thomas Edison, and it's a constant struggle, and that's happening in the background of our lives. It's not like at the forefront of anything. It's not as sexy as AI or blockchain or all the other interesting things happening in the tech world. But DC and AC are having what we call the war of the currents. There are residual effects of this, and it's being driven in large part by LED lighting. So LED lighting, we maybe take it for granted today, but it was just like 20 years ago when LED lighting was maybe the new kid on the block and accessible. We still have a lot of fluorescent lighting that we're retrofitting. And so LED lighting is a direct current powered technology. Also, wireless densification. So, wireless speeds are getting faster and faster and faster. So, with the advent of 5G, we have what's known as wireless densification. So, we need more antennas closer together, and that's all direct current powered and driven by DC. Think of the most efficient HVAC systems. Those are VRF, or variable refrigerant flow, or VFDs, right? Variable frequency drives. Those are DC motors. Anything that's variable frequency or variable flow is a direct current motor, a brushless DC motor. And so brushless DC motors are driving innovation in HVAC for more efficient HVAC, which is the largest energy suck in a building, is the heating and ventilation and cooling. And so the future of HVAC is also DC driven. EVs and fast charging, that's direct current. So level 3 fast charging is a direct current. It's the only way you can do it. And then renewables and microgrids, solar panels produce direct current power, batteries store it, and then we use it. So moving forward into the future, the world is changing to direct current. What's also happening at so this is from the bottom up, like our consumption. What's happening at the grid level is that the transmission grids are also moving to ultra high voltage direct current. So if you think of any new power line that's going to go up transmission level power line, not distribution, so not the local distribution grids, but the transmission grids, there's a break-even distance, I believe, of 600 kilometers right now, where anything above 500 to 600 kilometers has to be direct current. There's no way to do alternating current cost effectively. And so AC is getting kind of squished in the middle in the distribution grid as our consumption goes up from the bottom, DC, and at the transmission level, it's DC from the top down. And so AC is getting squished in the distribution grid, and that's likely where it'll live for the next, who knows, how many years until we end up changing that infrastructure. Um, So quick refresher, AC power alternates 60 hertz in North America, and it flip-flops between zero plus whatever voltage and minus whatever voltage. The commercial distributions are 600 volts, residential is 240, and it flips between these. Direct current power does not have a frequency. It's direct current all the time. That affords many benefits for direct current power, but a safety drawback. And this is why alternating current initially won the war of the currents, is because it has zero crossings, it crosses 0 volts, it's safer, and you can use it's safer with mechanical contacts. You can't use mechanical contacts with DC because there's no zero cross. And so your arc energy is very high. But we're in the 21st century and we have solid state switches. And solid state switches work very well with DC, and they're much harder to use with AC. And so this is part of the reason why the world is kind of flipping. We're in the digital solid state world. And so we're moving towards DC power. Converting from AC to DC is a very inefficient process. So because the utilities deliver AC to us, we have to convert it at the point of load. We don't do a centralized conversion and then at the service entrance and distribute DC. That would be great. And that's part of the work that we're doing. But for the most part, we have point of load conversions. So think of your cell phone charger or your laptop charger. That's what we're doing everywhere. We're doing it on our televisions, in our lights, um, inside of our refrigerators, like you name it. It's everywhere. Point of load conversions are inefficient and they waste power. Pick up your cell phone charger or your laptop charger when it's charging your laptop. Feel how warm it gets. That warmth represents a loss of power, and it's an inefficiency. What's sad is efficiency, power under 45 watts. So if you're doing a conversion under 45 watts, these are unregulated. And so there's no efficiency regulation. And so you end up with stuff that's 50% efficient sometimes, like these downlights from Amazon. If you ever buy downlights from Amazon or cheapo like downlights, these flat packs, the converters are oftentimes 50% efficient when you factor in the power factor losses. And so that's pretty sad that we're throwing away half the power. A lot of people don't care because these guys are, when you think of on a 1 unit basis, it's what, 5 watts? So what if you use 10 watts instead of 5? But when you think of a whole world of lights, it is a big difference. And we'll talk a little bit about what that means for the carbon intensity to the planet. And so here's a just an image that our someone from marketing made, and that's why AC power looks like a filing cabinet. But you can see the traditional AC layout is you have conduit and mechanical protection, junction boxes, and LED drivers. In a DC topology, class 2 low voltage, you're using low voltage cable, no mechanical protection, no conduit, no junction boxes. Everything is low voltage, and although you have more linear feet of cable because you have lower power runs, they're 100-watt class 2 low voltage circuits, you do end up with um, a higher overall lower cost because of the mechanical protection um, that you're foregoing on the job. And this lends itself also to another benefit for DC, is that you have centralized DC drivers versus decentralized AC drivers. You have this benefit now of removing the driver from the fixture or from whatever device, removing the point of load converter. Instead of it being on the device in maybe an inaccessible location, you can take all of these and move them into a centralized cabinet and do a direct current distribution to your DC loads. And so you avoid difficult maintenance. And sometimes these are devices are inaccessible and they're usually the first point of failure. So for LEDs as the example, because it's one of the it's the market that has the most traction right now. LEDs typically, if you see an LED flicker or just shut off, that's not a failure of the luminaire, the light engine, or the LED. That's a failure of the driver. The driver has failed, and those drivers they contain, if you can see my screen, they have electrolytic capacitors. And electrolytic capacitors, inside of these, there's an electrolyte, there's a fluid. And what happens is because these devices are inefficient, they generate heat, and this fluid will begin to degrade, like its properties will begin to degrade, and it goes into a thermal runaway. As it generates more heat, it becomes less efficient, and then generating more heat. Eventually, what happens is these they pop, right? And you see this if you've ever seen one of these fail, the cap that looks flat here, it'll bulge, right? And they know that it bulges, and so they create perforations. If you can see that, they create perforations because they know that's the failure mode. So it bulges there. And what'll happen when it bulges is the lights will start to flicker or they'll shut off entirely. And now the driver's bad. But the LEDs are fine. The LEDs are good for 100,000 plus hours. The failure mode of an LED is that it gets less and less bright over its lifetime. Um,
And so looking at that, oh, sorry,
yeah,
Bolis. And so
yeah,
looking at that side-by-side comparison, AC versus DC, and using your example of lighting, while lighting is typically located high up, are
yeah,
ladders involved? Is scaffolding involved?
for
Are
sure.
people's desks or equipment located under those
Yeah.
lights? How much of a pain is it to actually go correct all the lighting if you can simplify your maintenance routine?
It's exactly like what. So this is with Sport Check. So we did this one with Sport Check, and Sport Check didn't want the drivers all the way up. Like this is a very long escalator, so this is very high up, and Sport Check didn't want the drivers in this fixture. Also, it was hard to put drivers on the curved parts, so we ended up the lighting manufacturer just ended up putting the DC distribution in the stock room, and it's low voltage, so it doesn't have to go in an electrical room because electrical room real estate, everyone knows electrical room real estate's at a premium. So these can go anywhere. They can go in different closets. They don't have to go in electrical room closets. Um,
That's a good-looking
but
install.
yeah, oh, it could have been better. I'll show you a really nice one. Um, Basically, the problem is AC is CapEx and OpEx intensive. Line voltage installations are CapEx and OpEx intensive, but we do them anyway because there's no alternative. And the problem is all of you experience this problem, whether you're a lighting designer, architect, consulting engineer, interior designer, electrical contractor, like all of us experience this problem. And the problem, solving this problem means we can reduce the CapEx, project CapEx, keep our customers happy, and reduce the OpEx. These systems are more efficient, they require less maintenance. So it's oftentimes a no-brainer in a new build. For retrofit scenarios, it's a little bit of a different story, and we can get into that later. But for new builds, it's a no-brainer. Um, the solution is remove mechanical protection, remove BX, remove like your line voltage cable, remove conduit fittings. That's a lot of labor, junction boxes, putting it in labor, dollar sign, like all over the place, dollar signs, drivers, and then replace all of that with just low voltage wiring, driverless fixtures. Oftentimes, the manufacturers will provide fixtures at lower cost because they don't have a driver. And if you want to list later, there are over 1,500, maybe 1,200, over 1,200 um, listings, UL and ETL listings of fixtures, low voltage fixtures. I can share that list with anyone who's interested for sure. Um, so you eliminate junction boxes. It's faster installation, easier maintenance. You're reducing the labor. It's low voltage. It's safer. It's lighter. It's more cost effective. These are 25 pounds, these cabinets. 25 pounds. Like there's one behind me right now. But it's not just our system. There are so many systems on the market, and I'll go over what's available to you on the market. We're not the only one out there. There's a whole market, and what's happening now, the Schneider Electrics of the world, the Eatons of the world, they're starting to partner up with us and our like I call them our friends. They're not our competitors because it's an early market, and so I will share some of the names of also the other companies who are doing this. Um, there's also significant greenhouse gas reductions. If this is something that your customers care about, um, it's important to note that um, if you look at a baseline of just LED lighting, right, with regular wall controls, and you add direct current power also makes it easier to add lighting controls into the system and more cost effective. But for every kilowatt hour you conserve, it's about 0.85 pounds of CO2 emissions. And that's based on the carbon intensity of the US grid. So it's a little bit better in Canada because we have a lot of hydro. Um, but essentially, you can divert roughly 1 pound of CO2 emissions for every square foot per year when you use a direct current powered system. And you pair that up with really simple automation. Um, that's simple and to do in DC. Um,
Hey,
there's two
Bolus,
to yeah,
sorry, Bolus, before we get too far, there's a question that I didn't notice it at first. It popped up in the chat instead of the Q&A tab.
that's fine.
But Mark asks, um, and I can't remember at what point, what slide you were on, but Mark
Yeah.
asks, are they class 2 rated?
Yeah, so this is a class two low voltage system. So all of the equipment I'll be talking about from us or our competitors is all going to be class two low voltage rated on the first part of the presentation. The latter part of the presentation we'll be talking about class four and fault managed power rated equipment. So
Perfect.
yes, everything first part is class two rated. No problem, Mark, and thank you for the question. And yeah, feel free, guys, jump in if you have any questions in the chat, and I'll leave lots of time at the end for discussion. Um, there are two topologies when you're doing direct current power distribution for any type of device, whether it's lighting or not. So there's lighting in this example, but this also works for other things. So the two topologies is driverless topology, so a bus. You have a bus topology, or you have a point-to-point topology with an external DC to DC driver, right? And many people make this. So, for example, we just did a big project with Acuity, Acuity Lighting, if you're familiar. Acuity has a fantastic DC-DC driver that goes onto luminaires, and you deliver 57 volts to it, and you put these on a bus. But what it allows you to do is individually address the devices, or if you have devices at different voltages or current ratings. If you have devices that are the same voltage, same current, you can put them on a bus together. And so driverless LED fixtures is a fantastic example. And the benefit of that is you centralize all of your intelligence or your driving capability into the cabinet or PoE switch or whatever. We'll talk about PoE lighting. PoE lighting is one we'll talk about too. Um, and then these are hot swappable, located in a single cabinet, higher lumen per watt efficacy on the fixture because there's no driver. So your lumens per watt go all the way up as well. That's another thing, is you get higher efficacy for your luminaires. Um, and then if you have individually different fixtures or many zones in a room, for example, like we just did at a hospital, and the patient rooms have like 5 zones of lighting in the patient room. It's hilarious. But then the Acuity drivers were really good because they could individually address those drivers. And Watt Stopper has a lot of great, like we have a lot of experience with like Watt Stopper, Acuity and Light. Lutron has some good stuff too on the control side. There's lots of interesting stuff happening in the lighting space right now. With the decentralized drivers, you get greater control flexibility and addressability there. Um, This
So
is,
Bolis,
yeah,
sorry. So just so we're clear, when we're looking at the daisy chained option, that's when we
yeah,
have uniform, predictable
yeah.
loads. But if we want some variability, that's when we go to the decentralized.
A decentralized like driver, DC to DC driver based solution. And so, yeah, exactly. If you have multiple different devices that you want to control, um, like for example, like there's one job we're doing right now, which is a hybrid copper fiber, and it's going out to this remote device that's converting the hybrid copper fiber to PoE for security cameras that are beyond the reach of regular PoE. And so there's so many applications happening in this space. But yes, you'd use an end node or remote node, and I'll talk about like what these remote nodes do to control multiple different devices, or if you have a fiber cable to convert that back to copper. There's different uses of this end node, and for a more simple installation of uniform or like devices, you would do a bus, and these are wired in parallel, not series. You can wire them in series, but you can also wire them in parallel. That's the majority of stuff is wired in parallel. But for LEDs, of course, you can wire them in series. Um, uh, for typically, when you look at a class 2 low voltage system, the specs you'll be looking at are what is the input voltage, and what are the output voltages, how much power can it handle, and what control interfaces are there. So our system, for example, is it's modular, so 8 modules, they're 400 watts each. There's 32 circuits because class 2 low voltage circuits are capped at 100 VA or 100 watts per code, and 60 volts maximum, 100 watts maximum. So that's something you'll look for as well is what are the voltage ranges, and the power is going to be capped at 100 watts. You want to make sure that the outputs can go up to 100 watts. A lot of stuff on the market is going to be 96, 90, and that's one of the things that happened with PoE is it couldn't source 100 watts at the output end. Um, this system is 3 kilowatts or 3 kVA. And then control options, these matter more to lighting folks, but like dry contact is good for everybody. DMX and DALI is going to be more important for lighting. And then there's CAN bus. Ocean is I would say a dead protocol for wireless. And then there's expansion ports to do different types of stuff. But we've seen people do 0 to 10, BACnet, other types of wireless, etc.
Uh,
Um,
Bolis,
yeah,
before you go too much further, we've got a question from John. Probably
yeah,
applies to, yeah, there we go. Okay, so we're on that slide. Um, so John asks, are there different voltage selections such as 24, 60, 90 VDC? Now, I don't know if John is specifically asking about the Sense product that we're
yeah.
looking at or just generally in market.
Generally in market, so I'll answer like for like all cases. Most manufacturers, so for example, if it's PoE, if it's power over Ethernet, that's a fixed voltage. I believe it's fixed at like 52 or 53. And then most manufacturers will have different versions. The standard voltages in the market are 12 volts, although 12 volts is like I wouldn't recommend it because the voltage drop is going to be such a great percentage. 24 volts is the most common, which is weird to me because the code allows you to go up to 60. So why would you do 24? But the industry majority is 24 volts. So yes, there's a 24 volt. These are more like our system is programmable. Voltage and current is programmable and you can set it up to 60. But we have common voltages. Those are 24 volts. The majority of stuff out there, a lot of stuff is 24. 36. 36 volts is common because of these guys. Okay. These they're called chip on board. I'll show you if you can see my screen. These types of LEDs, they're called COBs or chip on board. Those are typically 36 volt devices. So 36 volts is another common voltage. And then, of course, 48 is a common voltage. And then my favorite, 57.5. Now, 57.5 is a great voltage because it's as close to 60 as you can get with while still remaining with the class 2 low voltage limits, providing some headroom. then it minimizes your voltage drop percentage and allows you to maximize your run length. Um, but it's a good question. These do come in all sorts of shapes and sizes in terms of voltage and current. Um, the remote devices, so PoE had one. There's DC to DC device. Basically, these are DC to DC converters that allow you to do an interesting thing. It allows you to take the run here, do this at 57 volts, so you can have really long run lengths, plug lots of these devices in, and then have different devices at the output. So PoE was called a PD or a powered device. They're also called DC to DC converters. Sometimes they're fiber optic cable in, copper output. This device, the one that we make, is just DC to DC, so it's an input of up to 60 volts, less than 100 watts, and then the output is settable. It can vary its output. This version is 36 volts, and so it'll go from 36 down to zero, so from 0 to 36, or I believe 24 to 36 in that range. 0 to 10 volts control, dry contact control. But many people in the industry make these, and the nice thing is that these devices, this is where you plug in your Lutron, your Athena wireless node or AWN, or your Watt Stopper wireless nodes, or your Nlight, your Acuity Nlight NPS 80 devices. And these plug into here, and now you can plug this into a Watt Stopper Plus control system or in Celium. You can plug it into a Lutron control system or Quantum or an Nlight control system, the Acuity Nlight. So there's so many flexibility integration options with DC power for different types of control systems in the buildings. Um, a lot of systems you'll also find have online configuration platforms. So WattStopper has a great one for configuration. Our platform is more about setting the voltages and currents. But every manufacturer now, the majority of them have these platforms where users, installers, people doing commissioning, all of them, they can go in and change anything on the system and reconfigure it. So setting the milliamps is either the milliamp set point. So in constant current, you put a milliamp set point, right? And then in constant voltage, you put a milliamp tripping point. So a point at which you want the circuit to act like a breaker and shut off when it passes a certain milliamps. Um, so these systems typically you'll find like not more than 4,000 milliamps or 4 amps. So 24 volts times 4 amps is going to give you roughly 100 watts. Um, and so that's what we do there. Every manufacturer has an interesting uh, like software for management these days. The UL certifications you should care about in this type of system. So there's UL 916 is the standard for safety energy management equipment. And so our devices are UL 916. And a lot of devices on the market in this space, in this DC space, will be UL 916. The other UL to care about is UL 2108. UL 2108 is the standard for low voltage lighting systems. That's for the lighting folks. Low voltage lighting systems. And we're at close to 1,500, maybe over 1,500 now listings between UL and ETL. So there's lots of on the market. And I have a list on Excel if anyone wants it. Please reach out for sure. But these are the two UL certifications that matter the most. Of course, there's the ones for emergency lighting. There are other UL certifications that are more nuanced for specific applications, such as telecom applications. But these are like 62368. And but these are the most important, 916 and 2108 for lighting cases. And then, of course, 62368 -1 is general safety for the telecom and data equipment. And so in terms of case studies we've done for this type of system, we have a few things. So Scotiabank, you guys will like maybe recognize the Scotiabanks at Eglinton and Yonge. We've done now 10 Scotiabanks this way. DC Power. We partnered up with a lighting manufacturer to do the facades. So the facades are backlit using DC Power. This was part of a sustainability pilot with the Scotiabank. And we also hospitals. So hospitals and medical office buildings are my favorite because we get to do all the lighting. So like all the general area lighting, we get to do direct current powered. So we partner up with Acuity to do a DC to DC lighting system um, on these hospitals and medical office buildings, mostly in California, although they are spread out across the states. And hopefully we'll do some in Ontario soon as well. Um, this is Sport Check. They're doing these like racetrack fixtures, and they wanted remote drivers. They didn't want the maintenance to be done in the ceiling there. Also, there's if you're interested, one of our competitors, Loom, they did in Texas with Mauser. They did a whole warehouse of down of high bays using class 2 low voltage. I don't quite agree with their approach. They did PoE for the they I don't know why they would use Ethernet, but I do agree with that you can do high bays. So HE Williams and Zumtobel, those are two manufacturers that have high bay fixtures with low voltage connections for class 2 low voltage. It's an interesting emerging application for class 2 low voltage. Instead of doing 347 volt AC distribution for high bays, or in the States they do 277 for high bays. We can now do low voltage cost effectively. So these are some options that exist on the market. So you have options like ours, these hot swappable systems, like the Sensel V Hub. You have power over Ethernet. You have regular LED drivers, so your standard LED driver, your AC coupled LED driver, and then you have people are doing this, which is cool. You put drivers in a box. It's not the cleanest approach, but it's low cost. And so if budget is a concern, drivers in a box, where you put all your line voltage drivers in a box. If you have a little bit more budget, something like what we build is a little bit cleaner and more it's easier to install. This is a bit more of a hassle, but is more cost effective if budget is a concern. So they put a bunch of these line voltage drivers in a box and then have the distribution going out to the fixtures. And you'll see some lighting companies that actually make a product like this. So like Vode Lighting, for example, has something called the Vode node. And who else? Alphabet Lighting has what they call DX, which is I guess stands for distribution, but like they have their DX system, which is essentially Eldo LED drivers in a box like this. And so you can see some stats here. I can always come back to this. This is a TD Bank at Square One, Mississauga with Viso Lighting. So Viso Lighting built this beautiful fixture, and the issue is where do you put all these drivers? And because this is all drywall, and you want to put it above the drywall, like it's not drop ceiling, right? It's a drywall. There's partitions and plywood, and so what we did is we put the hubs in the electrical room here, and just the electrician did a nice little feed there from the panel, the electrical panel, into this device. And then, of course, you can see low voltage cable, super simple tie straps. Like you treat low voltage cable as you would like Ethernet cable. Um, and yeah, nice and simple.
Hey,
Here's another
Bol
shot. Yeah.
Sorry, Bolis, before we get too far, a question came up and probably relating to that slide that had the UL logo on it. The question is about Canadian certification. Now I'm assuming maybe that's also could be a CUL mark.
Yeah. So these are all UL US and ULC. CUL. So these any UL that we talk about here is going to be Canadian and US. Our products as well. But the majority of manufacturers as well, they typically will go for UL and ULC and UL US. Just like at the outset. it's fairly standard for large manufacturers. But it's a good question because it does make a difference. Canadian UL is different than US UL. And you have to have CS because here our authority is the CSA. And so it does make a difference. So it's a good question.
Very good. And there is one more,
Yeah.
probably if you go back to there we go, that present slide. A question came in, if the drivers are in an enclosed box, Mark assumes the designers take thermal issues into account, like maybe adding fans.
Yeah, so it's a good question. And so because you have 3 kilowatts of conversion here, what we have first of all is we want to use the highest quality power electronics to make sure it's very efficient so that we don't have the problem in the first place of high heat. And we can afford to do that because we're doing it in a centralized location. We don't have, instead of having 32 or more drivers spread out where we can't balance. They have this thing that it's a triangle. The power in power electronics, there's a triangle. We have to balance cost, efficiency, and power density or physical size. So because here we can play with physical size, we can have a physically larger product. We can keep the cost low and the efficiency high. And so that's something that is one of the reasons how we can keep the heat down. But we also include 3 active cooling fans. So there's one down here with the rectifier. It's an actively cooled rectifier, and then you have 2 more fans at the modules to move away heat. And there's a temperature sensor, and these are not on all the time. They come on as needed to allow air to flow. But it is a good question for heat management, of course. Just another shot of like how like just show flexibility. Like sometimes electricians and this is not just our system, like any system, you can wire these. This is class 2 low voltage. You can wire it any way you want. So twist lock, for example, you can use a twist lock. You can hardwire it to the hub. There's another shot. Oh, right here. He has switches like just regular on off switches like single pole switches there. I don't. This one's not the prettiest one, but whatever. Like at the end of the day, they were trying to save costs, so just BX to these switches. Um, this is a typically what they'll do is a 208 volt feed. So this will be 208 AC. In the US, it's 277. In Canada, we use 208, 20 amps. So they'll use one breaker. So one 20 amp breaker or I guess double pole. 208 is going to be double pole breaker to feed these. This is another Scotiabank. This is Bloor and Young, I think. They did these blade signs. Like I think there's 140 of these. So this one has 12 kilowatts of DC lighting around the branch there, and yeah, and this is in the ABM room. Um, so that you can, it doesn't have to be the electrical closet. You can go in the where the ABMs are. It's flexible. So this is like an ABM on this side. Um,
Now, Bola, speaking
yeah.
of pretty installations, if we go back to that electrical closet or the Mississauga TD Bank,
Mm,
there was a question, and you know you decide, or I'll let you answer.
yeah.
But the tie wraps, are they the ones that we see in these photos? Are they approved to support those cables?
Yeah.
Okay.
Yes, this is to code. Yeah. I mean, the inspector comes and see. So like, yes, this is to code. This is low voltage cable. This is like, this is you can treat this like they use J hooks. So this is like think of this as Ethernet cable, right? If this was data cable, right, would this be appropriate? A lot of people would say yes. So from a code perspective, it's electrically safe. This is virtually free of any shock or fire hazard. So then it becomes up to the installer, right, and the customer how much money they want to spend on the appearances and the rest of the things. But is this safe? Yes. Is this pretty? No. It's not. And there's probably better and cleaner ways to do this, as I'll show you. But yes, this totally is safe, and the inspector will come on site and take a look at this stuff prior to closing out the permit.
Now,
Um,
speaking of
yeah.
inspections, do you find that most inspectors, all inspectors, or a good majority, are familiar with what they're looking at?
Yes, but if they're not, they contact us. A lot of times people will have a beef with power over Ethernet. If they see PoE, they like there's always like a whole issue with power over Ethernet. There's a long history behind the unions and like the issues there. Ontario's an interesting player because we have the OESC or the Ontario Electrical Safety Code here, and in our code book, even if it's low voltage, has to be installed by an electrician. Has to be a licensed electrician installing the luminaire. Um, doesn't matter. But in other jurisdictions across North America, it doesn't have to be an electrician. It could be a licensed electrician. It could be anyone. It could be journeyman, apprentice. It could be someone else doing the installation. Um, but usually, electrical inspectors see no issue. This is wall-mounted equipment for them. They see this as a like lighting control panel. Or in the case of HVAC, when we're doing HVAC jobs, they see it as a ventilation control panel, or HVAC control panel. So they look at this and see a control panel. So they're typically okay with this. It's stuff they've seen in the past. It's just getting a little cooler. Um, I'll skip through some of these so we can get to the. Oh, this is one of my favorite installations. So you'll see here they put the this is a medical office building. They put the emergency feed on a separate hub. So they have emergency lights going separately, and then they have the normal lighting on a feed like this. You have the panels here on a 208 120. So you're and then this is 277. They have a 277 feeder, and so these are fed by 277, and you have your outlets fed by 120. And so this is nice that they eliminated basically AC power line voltage from the ceilings. Now they have AC voltage just limited to the wall outlets in this building. So this is a nice one. Um, this was like a medical office building, but we're doing a hospital similar size. Um,
And again,
that's all the
Bolis,
class two. Yeah,
sorry, before we get too far, a question from Mark. Is
yeah.
there a specific type of wire that's employed in these types of installations? For
Okay.
example, Cat 1. Is the wiring plenum rated?
So okay, good question. So specific type of wire, like not really. There's so many different types of wire. These are low voltage, so 16.2, sometimes like these are 16.2, or sorry, 14 rather. These are 14.2 plenum rated cables because they are going in the return air plenum. They are plenum rated, but these are 14.2 and they're going considerably long. I've seen people use 18.2, so number 18 cable also works. Typically we see number 16, 16.2 or 16.4 or 16.6 or 16.8. It depends upon what you want. And so you'll see here these are I believe 16.8 if I'm not mistaken here, but here they'll use 16.2. Rather, these are 14.8. 14.8. So you'll see people use different types of low voltage wire. Sometimes it's thermostat wire. Sometimes I've seen speaker wire, although I wouldn't go for speaker wire because lots of thin strands. But there's so many wire options as long as it's low voltage rated. And if you're going in the plenum, of course you want it to be plenum rated. And if you're going in the riser, you want it to be riser rated. Um, and so but that's the wire there, but I can touch more on that. Just in the interest of time, I'm going to jump to the class 4 stuff. This stuff is interesting, but of course if there's any question that wasn't answered here, please like feel free to reach out. I'm happy to answer any questions about DC power. It's my passion to talk about DC power. um, so this is new. In 2023 the National Electrical Code introduced class 4. Okay. So we don't have class 3 in Canada. That's a US thing. Class 3 is basically special case of class 2. Um, Oversimplification, but anyways, this is cool because class 3 was introduced in 1978. So it's been 45 years and now they're introducing class 4. So what's going on here? It's really cool. It's what's known as fault managed power. It's basically you use low voltage wiring practices. Like here's a fault managed power cable, right? It's twisted pair. It's twisted pair cable, but you can do 400 volts, and there's no limit on power as long as you respect the ampacity of the cable. Um, and so it's making its way to the Canadian Electrical Code. It'll be in the next code cycle. We'll have class 4 in the code book. So that's exciting for us in Canada. Um, so class 4 system, what does it do? It monitors abnormal conditions. It's basically a fancy circuit breaker. Okay. You can intentionally short circuit the system at 400 volts DC. Human skin, if you contact the parts by accident, you might feel it a little bit, but it'll shut off before it hurts you. So electrical shock is not a hazard. Ground faults, no hazard. Overcurrent, no hazard. And as I said, intentional shorting. So they want it to be so safe that if someone is working on the system and they don't know if the system is energized, they have to be able to intentionally short circuit the system and ensure that the power shuts off. So it's pretty robust stuff. The UL certifications, UL 1400-1, that's the outline of investigation. So it's not yet a standard, hasn't been turned into a standard. It's the outline of investigation for fault managed power is -1, and the outline of investigation for fault managed power cables is -2. Um, and so UL, this is what UL is doing right now. We're also on the technical subcommittee for CSA, bringing this to the Canadian Standards Association as well. And the IEC will follow suit. And hopefully we have a unified standard across North America at some point. Um, this is cool for telecom because you're taking 48 volt cables. If you've ever seen a telecom 48 volt cable, actually, I have one. I have a picture, I think. This guy right here, 48 volt telecom cable. That cable right next to it is carrying the same amount of power because you're instead of having 48 volts, you have 400 volts, right? And so you're 10x the voltage roughly. And so you're cutting the current by a factor of 10. You're decarbonizing uh, quite a bit. And so there's significant greenhouse gas reductions in the embodied carbon. If you think of a 100,000 square foot building, if you're looking at cutting essentially the copper in half, and what that means is you're gonna have an 8% roughly reduction in the embodied carbon in that just 100,000 square foot space. So pretty relatively small commercial building. Um, and you can cut that copper usage by half, but that doesn't just mean the embodied carbon, that also means the cost. The cost is also being cut in half. This is an emerging technology, so still early days. Um, but we're currently one of 4 manufacturers, so there's only 4 manufacturers globally producing this. Cisco is really interested in this, so they released this. If you ever want to check this out, Cisco released a study on fault managed power, and they've partnered with one of the manufacturers, Panduit, to bring this stuff to market. And so this is Cisco and Belden also makes, this is a Belden cable right here. So Belden makes this, Superior Essex makes it, Prysmian makes it, General Cable makes it. So all of the big cable guys, they make these cables now because they're excited.
And
And
they
so
probably, sorry, they probably wouldn't be making
yeah.
those cables if they didn't think it'd be going anywhere.
Oh no, no. Yeah, this is like I mean look what Belden. So this is Belden right here. Um and so yeah, Belden, Prysmian, Remy Cable, like you name it. Like there are more cable manufacturers on this than there are systems available. So the systems typically look like this. So I'll show you some other ones too, but ours it's a rack mounted equipment and wall mounted mix of the two. Um an R flavor of class 4, it's 4 channels, 3.2 kilowatts per circuit, using cable like this. You get 3.2 kilowatts per circuit, so it's significant. It's because you're using 400 volts to do the transmission. VoltServer is another provider of these systems. They're the pioneer. VoltServer was like the first one. They really like created this market. They were the first one in the market. Their system is quite different than ours. It's a much lower power. So they have a different target market. We're targeting higher power applications. We're the only Canadian manufacturer. The rest of the guys are American. So Panduit and Volt server pretty much have the same, almost identical system. Lots of channels of low power. Um, but you can take a look and see what they have to offer. It's pretty much, again, they're all at this point, it's early days, they're all pretty much the same and following a standard. Um, and the differences are going to be in the power levels that people play and the different markets that they target. Um, Interesting application, again, hybrid fiber copper. So for very long runs. So lots of telecom applications. So some of the stuff is hybrid. Data center applications. So this was a really crude early drawing, but it's the only one I could find to show the future of PDUs and data centers. So we might be going back to DC PDUs in data centers and having class 4 zero use solutions for the data center. Um, this is a just for those of you interested in numbers, this is a chart of what class 4 is capable of doing in terms of distances. So over a kilometer, you can see how much power you can get receive over at a kilometer of distance. I Forgive me, this is millimeters squared because this was prepared for one of our European stakeholders. But I believe it's um, if I'm not mistaken, this is number 12 cable, 14, 16, or it could be, yeah, number like 12, 14, 16, 18. Or other way around, sorry, 12, 14, 16, 18. Gauge cable. And so I can also share that. This is the last slide. I wanted to leave at least 10 minutes here for questions, but happy to also take things offline. Or I'll leave the deck here so I can flip to any slides as questions come in. But also, yeah, if you ever have questions, reach me on LinkedIn. I'll drop my email in the chat here. Um,
Yeah, we haven't had any new questions come in.
yeah,
But it was great. We had a whole bunch of people participating throughout with their questions. So maybe you've just completely answered everything, and the future is here today. Everyone's going to switch over to
yeah,
DC power.
yeah.
Meantime, I see, Bolis, you have put up your email in the chat. That's excellent. One of our attendees is asking, will the slides be available afterward? Uh, Bolis, any issues with sharing the slides? Do you want people to
No,
contact you or to go through me?
as you guys see fit, like whatever. Yeah, but like happy to share.
Okay, perfect. So Mel, in answer to your question, yeah, just contact Bolus by his email there, Bolus Ascends Power, and he can hook you up with the slides. Again,
Mhm.
as a reminder, my email is at the top of the chat for certificates of attendance. Just send me an email and we'll get that furnished for you. And before we wrap things up, maybe just give it, another 20 seconds in case anyone is furiously typing a very interesting question. But if not, um, then again, there was that reminder about the certificates of attendance. After a time, this session, which was being recorded, will be uploaded to Electrical Business Magazine's website. And so, if you did miss anything, if you didn't get the slides, um, there will be that. Oh, perfect. And someone has indicated that they want to connect with you on LinkedIn. So hopefully, Willis, you get a whole bunch of connection requests after this session.
Yeah, for sure. Yeah, if anyone, yeah, for sure. If anyone has any questions about anything you saw today, or in general, or you just want to brainstorm, or it's something you want to learn more about, always happy to talk more. Also, the engineers on our team, like, all love talking about the technology and the what's driving this change in the world. But I appreciate all of you for like coming out and listening. And it's an interesting thing, and I hope you spread the message about DC power and the way it's decarbonizing the planet and saving us energy, reducing our capital cost for projects and our ongoing total cost of ownership.
Now, I seem to recall before I let you go, wasn't DC Power somehow involved with the Leadership in Energy and Environmental Design rating system?
Yeah, yeah. So there was a lead pilot credit. I'm not sure if it's still around, but there was a lead pilot credit for if you did DC power in buildings, you get lead points. I think it was up to 18 points. It was significant. Like it was a significant number of points, but I'm not sure what they did with that, but it was a pilot credit. Yeah.
Hmm. Interesting, interesting. Uh, okay, one last question, and then we'll close it off with Mike. So Mike asks, what are the current strategies and regulations surrounding emergency power systems and distribution? Are standards in development?
Um, so for emergency power, it's the same standards. So Canada has one and US has one. I think UL 924 is in the US. And then we have one here. I might be getting them mixed up, but it's the same standards. The UL 916 energy management equipment standard has provisions for what you would do with the emergency lighting. And most of what it is, it's about controls. So if it's UL 916, what you got to do on this side, on the remote side, is make sure you have a emergency rated controller. And it's more about the controls. It's more about like the if there is in the case of an emergency. So for example, there's like a dry contact here. So it can take a dry contact as long as your system can take a signal from, for example, the fire alarm or the emergency inverter, the lighting inverter, and it can take that signal and go like, okay, it's emergency, and then go into an emergency mode where, for example, your only the emergency lighting is coming on, everything else is shutting off. Then yes, you can get compliance for emergency. So it's not standards development; it's more about the implementation, how you do it on the project.
Very good. And if there are additional questions, we have Bolis's contact information. He's on LinkedIn. We've got his email there in the chat. So feel free to reach out to him. As he said, he's passionate about this topic, as are his colleagues.
Hmm.
Happy to chat with you further offline. Meantime, Bolis, I appreciate you coming on to deliver the good word regarding DC power,
Yes,
and I expect over time we're going to see more and more of that. And to everyone who signed up, thank you for coming and attending and bringing those questions for Bolus. And I wish everybody an excellent Monday. Bye bye now.